Now, a few important terms that you need to understand in order to understand how we do research in psychology. So, like I said, we have theories. We develop theories based on a lot of evidence and research support. And these theories are overarching summaries or explanation of phenomena. For instance, we might have a theory that sleep improves memory. Now, this is a very broad. This doesn't necessarily specify what we mean by sleep, what we mean by memory, things like that. It is an overarching theory that summarizes the research on the relationship between sleep and memory. It also explains the differences that we see in our memory when we're able to sleep and aren't able to sleep. Now, from these theories would develop hypotheses. Hypotheses are testable predictions based on a theory. So a theory is overarching, it's very broad. A hypothesis is going to be much more specific. It needs to be testable. It needs to be small enough so that we can test it pretty easily. So, for instance, out of this theory that sleep improves memory, we might develop the hypothesis that when people are sleep deprived, people remember less from the day before. Now, this is very specific because we're talking specifically when people are sleep deprived, and we're specifically saying that we're saying that they remember less from the day before. So you can see how these tie to the concepts of sleep and memory, but they're much more specific than the theory was. Now, even more specific are operational definitions. Operational definitions are the exact descriptions of what we are testing and how. So this is what we are going to actually test in our research study. So my hypothesis is that when people are sleep deprived, they'll remember less from the day before. So specifically by sleep deprived, I mean getting 2 hours of sleep in a night instead of 8 hours of sleep in a night. So that is what I mean by sleep deprived. Now, I could alternatively say that sleep deprived is only getting 6 hours of sleep for an entire week. Now, we would generally say that that's kind of sleep deprived. I could say no sleep instead of 2 hours of sleep. So an operational definition is an exact description of what I'm studying, what I'm actually going to be testing. So hypothesis of when sleep deprived, 2 hours of sleep, people remember less from the day before. Now, just like sleep, remembering less is still a little bit broad. So we have to define what we mean by remembering less from the day before and how we're actually going to test it. So our operational definition for memory is remembering a list of 20 words that were presented the day before. Now, I could do memory for a passage. I could do memory for a group of items that you looked at and how many of those you can remember. I could do memory for pictures that you saw. I could have you list the words and say, these are the words that I saw the day before. I could ask you, did you see this word, and kind of go on your recall memory, or being able to identify the words that you had seen before versus words that you didn't. And so my operational definition here is being able to remember a list of 20 words that were presented the day before. So you can see how it goes from theory to hypothesis to these operational definitions. It becomes much more specific as we go so that we can do this study. Once we've done the study, and we'll say in this hypothetical situation, our research study supported our hypothesis, which supported our theory, we also want to be able to replicate those findings. So replication is repeating the original observations with different participants, materials, and or circumstances. This is our ability to say, even when we have new participants, we found the same thing. So this finding holds up. Non-replication is the inability to repeat the same results. So an example of non-replication is power posing. So if you want, you can go and look at the TED Talk on power posing. And this whole power posing thing was a really big deal, and this was a really interesting finding, but it has never been able to be replicated. Now, what this suggests is either that first study was a fluke and power posing doesn't actually have an effect, or it could be that the replications that have been done since then didn't accurately reproduce the original study. Because going back to our sleep and memory performance task, maybe instead of doing memory for the list of 20 words that you had learned the day before, we were testing your memory for information that you had learned in class in, say, the previous 3 weeks and how you perform on an exam. That might not really reflect the effects of sleep on memory. That could reflect more the effects of studying and things like that. So maybe the replication that we didn't accurately reproduce the original study. For instance, if I'm studying stress, maybe the original study had people giving a speech, having to give a presentation in front of other people in order to stress them out. But the replication tried to test stress by just having people write out an essay that they might give, which wouldn't be as stressful. And so maybe the reason that we weren't able to replicate the effects of stress was because our stress task wasn't actually that stressful. So when we're looking at replication, we want to be able to repeat the same results or repeat the same study to get the same results and make sure that we're doing it appropriately. Make sure that we're actually testing the same things. Now, another important part of research is meta-analysis or meta-analyses. A meta-analysis is a statistical analysis that combines all of the previous studies. So there are going to be lots of different studies, for instance, on the relationship between bullying and depression. And this meta-analysis is going to go through and say, okay, here are all of the studies that have been done on the link between bullying and depression. Some of them have found that bullying does predict depression. Some of them have found that bullying doesn't really predict depression. What is the overall picture? And so we can take all of these smaller studies that were done and combine them into one big picture that allows us to see an overarching view of what the research says. So that's basically how the scientific method works. So we develop the theories, we develop hypotheses off of those theories, we use operational definitions, we run the studies. Once we've run the studies, we may modify our theory, we may replicate those findings that we did. But how do we actually do the research? So now we're going to move into the actual research methods or the practices that we use, the different methods that we use in order to do research in psychology. Now, I can break these research methods down into three main purposes. We can have descriptive, correlational, and experimental research methods. So descriptive research methods do exactly what it sounds like. They describe behaviors. So we're not getting any relationships. We're just saying, okay, what is the frequency of marijuana use in teenagers? What does schizophrenia look like? So this describes the behaviors. A correlational studies looks at associations between two or more factors. Now, we can't say any kind of cause and effect because we're just looking at associations. I'll talk a little bit more about this later on. But we're looking at associations between two or more factors. So, for instance, the correlation between IQ and SAT scores. So we know that people who have higher IQs tend to have higher SAT scores. So we're looking at the link between those to see how do they move together? Are these two variables related? And then finally, we have experimental studies. Now, experimental studies actually you actually manipulate a variable. So you actually change something in order to hopefully understand cause and effect. What this does, allows us to say variable A, factor A, actually causes factor B. So for instance, if we're looking at sleep and memory, by modifying the amount of sleep that people get, I can change how well they remember things. And this allows me to say that sleep definitely affects memory. Now, our correlational studies were not really able to do this. So, for instance, if I'm looking at the relationship between depression and bullying, I can't necessarily say that bullying causes depression. So, that's a correlational study. Now, I'll talk about more about the difference between these correlational and experimental studies and why it is that experimental studies allow us to give this causal explanation a little bit later on. So, the first method I'm going to talk about is case studies. Case studies are in depth examinations of one person or of a small number or group of people. Case studies are actually relatively uncommon in psychology. We see them a little bit more in the medical field, but we don't see them too much in psychology. We do occasionally see them in things like applied behavior analysis. So, if we're looking, for instance, at treatment programs for children with autism or things like that, we see case studies occasionally. Case studies aren't used very often because we'll talk more about later on about representative samples. Um, but it's hard to say that one person represents everyone. Now, with these case studies, we're either hoping that the participants that we go in depth on are representative or do reflect everybody else, or we're using a case study to describe an unusual presentation of something. So we might have a person with schizophrenia who has a very odd presentation and odd symptoms. On the right here, you can see the cover for the book, The Man Who Mistook His Wife for a Hat. This is a book by Oliver Sacks, and Oliver Sacks was a neurologist and wrote several books on unusual cases that he had seen in his neurology practice. One of these books was actually turned into, or one of these cases was actually turned into the movie Awakenings with Robin Williams several years ago. So these are case studies because they're looking at unusual cases. Now, with case studies, we have to be really careful because, as we say in research, the plural of anecdote is not fact. What this means is just because you know one example of something doesn't mean it's true for everyone. We see all the time people who live to over 100 years old, and when they're asked to explain or what is their secret to living so long, they'll say alcohol and cigars or something like that, which we know statistically are actually associated with a shorter lifespan. And so just seeing these individual cases is not actually going to necessarily be representative of how things are for all people. So case studies we use occasionally, but we have to be careful when we're using them. Next up is naturalistic observations. Naturalistic observations are used to record behavior in natural environments. Just like with case studies, naturalistic observations only describe behavior. We're looking to see how often a child with ADHD gets up from his seat in the classroom every single day. We're looking to see the frequency of grooming behaviors in chimpanzees. So we're looking to see the frequency of behaviors or to describe those behaviors. A few examples of naturalistic observations are the primate research that is done by Jane Goodall. We use naturalistic observations to look at parent-child interactions to see, do parents and children have a hostile relationship? Do they have a really warm and supportive relationship? How does their conflict look? Kind of observing those behaviors to see how the actual relationship is. We can also look at naturalistic observations to test conversational distance. So the distance, how far apart people stand when they're having a conversation. Now we see this very stark difference in conversational differences between different cultures. So in the United States, we stand much farther apart than people from many Asian countries do. And so we can use this naturalistic observation by standing back and just watching people behave in their natural environment. Here we have one of the most commonly used methods used in psychology today, and this is surveys. With surveys, we ask participants to report on their own behaviors, opinions, and experiences. Now, surveys can be used to get descriptive or correlational information. So we can, for instance, down at the bottom, you can see how many people in your household use blank product. So that would be descriptive. Or we can look at correlational. So how likely are you to recommend something? We can look at different characteristics and how that's related to recommendations. We can also look, and this one's really common when we're looking at psychological disorders, is asking people to report on their symptoms. So over the past 2 weeks, how often have you felt anxious, or how often have you felt sad? Now, surveys are going to be highly dependent on the wording. So when we have to be really careful when we're making these surveys, using terms like gun safety versus gun control can really change the way that people view a question. So if you ask people how they feel about gun safety, most people will agree that it's important to be safe around guns. We can use the same exact legislation, but phrase it as gun control, and a lot more people are against it. We can also see this example in car crash versus traffic accident. If you ask people if they've ever been in a car crash, that's going to bring up a much more violent image, so a real accident. Whereas if we talk about a traffic accident, that might go more into fender benders, that could go into hitting objects that are not cars, things like that. So what the wording that we use on these surveys is really important, especially because we're not directly interacting with the participants. It's entirely dependent on the wording that we choose in the surveys. Finally, we have experimental studies or experiments. Experiments are unique compared to all of the other methods that we've talked about because experimental studies allow us to determine cause and effect. What this does is it enables the researchers to isolate the effects of one or more factors. So to definitively say A is caused by B. Now, we can do this by manipulating the factors of interest, by changing the levels of variable A, and by holding constant or controlling for other factors. Now, we do this primarily through random assignment, which I'll talk about a little bit more, but we can control for other things as well. When we're talking about experimental studies particularly, it's really important to understand a few different terms. And these are the types of variables that we're looking at. So variables are the factors. These are the pieces that we are looking at in order to test our hypothesis. So we have a few different types of variables. So the independent variable, also referred to as the IV, is the variable that is manipulated or changed. So if we're running our hypothesis about, if we're testing our hypothesis about how sleep impacts memory, our independent variable is the one that we're changing. This is the one that we're saying has the effect. This is our cause. And so our independent variable in this case would be the amount of sleep that a participant is allowed to have. Either 0 hours of sleep, 2 hours of sleep, 8 hours of sleep. Our dependent variable, or our DV, is the one that changes according to the IV. So it is dependent on the IV. So our dependent variable is memory. This is the number of words that they remember from the list. So our dependent variable, how much they remember, is going to be dependent on the amount of sleep that they had. So our dependent variable is dependent on the independent. The confounding variables are any other factors that could influence the dependent variable. These are other things that could be causing our difference. So for instance, we may want to make sure that we control for how much sleep the participants got the night before, their general memory abilities, whether they have other mentally taxing things that they did later in the day or if they just relaxed. So for instance, we might control for this by telling all of our participants to make sure that they got a really good night of sleep before the study, or telling them not to do anything mentally taxing the next day. So we might have to make sure that we do this study on a weekend or during the summer or something like that. We might also have to look at their general memory abilities. So we may want to make sure that we test people's memories ahead of time. And we have some people with really good memories and some people with really bad memories in both of our groups, in both of our sleep groups, because otherwise it could be that people in our sleep group performed better on the memory task, but not because they got more sleep, but just because their memories were better in general. So we want to make sure that we have equal numbers of people with good and bad memories in both our 2 hours of sleep and in our 8 hours of sleep group. Now, another important thing to be familiar with when we're looking at experimental studies is called placebo. Now, this is going to be most important when we're looking at some sort of treatment. Now, the placebo effect is when something works just because we think that it will. So, for instance, most headache medications work not because the headache medication works, but because we think that it works. So, if you have a headache and I give you what's called a placebo, a sugar pill, and it's just a little pill made out of sugar that looks like headache medication, your headache will probably go away. And this is just because we believe that it will. We have the same effect if you drink coffee regularly and you drink decaf coffee when you think that it's caffeinated. You'll actually feel more alert. And this is because our minds are really powerful. So just thinking that something will work makes it work a lot of times. So, what we have to do in order to make sure that treatments actually work, not just because we think they do, but because they really do, we have to complete what are called placebo controlled studies. This is when we test how well a drug works compared to a placebo. So, if the drug works better than a placebo, there's a real effect. So, for instance, most people, their headaches will go away if I give them a placebo. But some people won't. Some people have a real headache that needs a real medical change. And we see that headache medications are good at treating those kinds of headaches. So, headache medication does work better than placebo. And we see similar things when we're looking at, say, antidepressants. Antidepressants work pretty well just based on our thinking that we're taking antidepressants. But we also want to make sure that they have an effect above and beyond that because medications come with side effects. And we want to make sure that if we are giving a person a medication that has side effects, that it's going to work better than just giving them a sugar pill and convincing them that it's real medication. When we do placebo controlled studies, we have two different groups. We have our experimental group. This is the group that gets the actual medication or the actual treatment. And then the control group gets the placebo. And we make comparisons between the experimental and the control group to see, does the experimental group get better more than the control group gets better? With those placebo controlled studies, we often have to take it a step further. We have to do what are called blind studies. Now, blind studies, the participants don't know whether they're in the experimental or control group. Now, this is because if I give you a sugar pill and I tell you it's a sugar pill, you're going to know that it's not going to work. So we need to fake people. We need to trick them into thinking that it could be the medication. And this allows us to see if the drug works better than just the placebo. So the blind studies don't let the participants know whether they have the real drug or the placebo. So we don't tell them if they're in the experimental group or the control group, which leads them to think, oh, I'm taking this medication. I might be in the control group, but I could also be in the experimental group. So we can get that placebo effect and we can see if the medication works better than the placebo. Now, sometimes we want to take it even a step farther than that and do what are called double-blind studies. This is where neither the participant nor the experimenter knows whether the participant in the experimental or the control group. And this is in order to make sure that the experimenter doesn't bias the results. Now, usually this happens subconsciously, but if a researcher knows that a participant is in the placebo group, and the participant says, yeah, I'm having these stomach side effects. I'm having a really upset stomach because of this medication. The experimenter might think, oh, I know that they're in the placebo group, and I know that there's a stomach bug going around, so I'm just going to assume that it's due to a stomach bug rather than a side effect of the medication. Now, if the experimenter, now usually the experimenters are not going out of their way to try and bias the results like this, but it could be subconscious. Even just noticing that a child is behaving aggressively. The parents might think that the child is doing better, but the doctor might say, no, they're not actually doing better. And that's because the doctor has, and they have the knowledge that the participants in the placebo study, so that they shouldn't be doing better. And so these kinds of things can happen. We have a little bit of placebo effect on the doctor's side as well, and so, or on the experimenter side as well. So we need to do these double-blind studies. Now, most of the studies that the FDA does, most of the studies that are tested on medications today are double-blind studies in order to make sure that the experimenter, that the doctor who is conducting the study, doesn't bias these results at all, doesn't convince themselves that, oh, it might not be a side effect, it might just be because it's flu season, or there's a stomach bug going around, or everybody has allergies right now. Instead, treat them as though they could be legitimate side effects of the medication. And this is really important, to particularly when we're looking at side effects, because we want to make sure that we're actually recording side effects of the medication, and not biasing those results, not just that the medication works, but the number of side effects that we get from those medications. Now, who is it that we're actually studying? So a couple terms, population and sample. The population is everyone. This is everyone who could possibly qualify for your study. So if you are looking at the effects of sleep on memory, you are making a general claim that sleep affects every person in the world's memory. So our population in that case would be everyone in the world. If we're saying that college students do better on exams when they sleep, that would be everyone in college. If we're looking at how a medication or a treatment works for depression, we are interested in everyone in the world who has depression. So our population is everyone who would possibly qualify for our hypothesis or our theory. And the sample are the people who are actually in the study. These are the 50 or 200 or 20,000 participants who actually participate in the study and we collect data on. Now, a representative sample is ideal. This is when the sample, the people who are actually in the study, are representative of the population. A truly random sample means that everyone in the population has an equal chance of being in the study. Now, this is incredibly unusual. It's really hard to get a random sample because let's say I'm talking about peer relationships in adolescence. I am assuming that every single adolescent in the entire world could be represented by my sample. Now, if my sample is only collected in the United States, or let's say my sample is only collected in New York or Alabama or Arkansas or Florida, that is not necessarily a representative sample because the adolescents that I see in New York City are going to be different than the adolescents that I see in a rural town in the Deep South. So I need to be careful because what happens then is I have what's called a biased sample. That means the sample does not reflect the population. So this affects my ability to say that the findings that I found in my study are true for everyone. So a bias sample is what we have most of the time, honestly, and it's not ideal, but we do as best as we can to make as representative of a sample as we can. So a bias sample would be if I only recruit from one country or from one school, or if I only recruit people with depression who are currently being treated by a psychiatrist. So if I'm saying that a medication works for depression, it's really hard to tap into every single person in the world who has depression. Even if I'm only looking at people who are currently getting treatment, that is a very select group of people with depression. That is people who have the resources to go and get treatment. It's people whose depression is severe enough that they are seeking treatment. It's people whose depression is not so severe that they can't even make it out of the house to the psychiatrist's office. It's people who believe that medication will work. And so this is a bias sample. And even if I try and collect people who have depression, who are seeing psychiatrists all over the world, it may not be reflective of every single person in the world who has depression. So I have to take all of this with a grain of salt. Now, for the most part, people who have depression, who are seeking treatment, and who are not seeking treatment are biologically going to be pretty similar. So my ability to say, okay, this medication works for people who are currently seeking treatment, I can probably say it will work for people who will seek treatment in the future. And so my ability the usefulness of it is still there, but we want to make sure that if I'm talking about college students, I want to make sure that my sample is going to reflect all college students. I don't want to only collect data from a party school like the University of Florida versus a small liberal arts college like Lyon College. And the differences between those two schools are going to be pretty great. So it's important for me to make sure that I pay attention to those. Now, once we've collected our sample, once we've recruited all of our participants, we want to randomly assign them. So this means that I'm going to put participants in the experimental or the control group completely at random. So I'm basically going to flip a coin for each participant and say, okay, heads, you're in the experimental group, tails, you're in the control group. And what this does is it controls for individual differences between participants. So like I said earlier, when I was talking about the effects of memory, and some people have better memories than other people. Now, in theory, this is not always in practice, but in theory, by randomly assigning people to the experimental and the control groups, or to the group that gets 8 hours of sleep and the group that gets 2 hours of sleep, by flipping a coin for each participant, I should be putting roughly equal numbers of people with really good memories and people with really bad memories in each of the two groups. And so that's why it's really important to do this random assignment. Now, how do we know which of our research methods to use? This is really based on our research questions. So a refresher on the three different categories of research methods. We have descriptive, correlational, and experimental methods. So remember, descriptive methods are going to describe the behaviors. We can observe behaviors, we can record behaviors, we can ask people to report on their own behaviors. We can use a case study and describe an unusual presentation of schizophrenia. We can ask people to report how often they exercise. We can use correlational studies to look at associations between two or more factors. So if I'm looking to see how IQ and SAT score are related, these are naturally occurring relationships. I'm not manipulating anything. I'm not assigning people to a particular IQ score. I'm not assigning people to a particular SAT score. I can't do that. That's not possible. What the correlational does is it allows me to know how well one variable predicts another variable. So I know that IQ predicts SAT scores. I know that people with higher IQs tend to get higher SAT scores. Now, this is not saying that IQ causes SAT. There's a lot of other things that go into your SAT score, how much you practice, how good your education was up until then, but IQ does play a part. And so we can predict people's SAT scores based on their IQ. We can predict people's college freshman GPA based on their SAT scores. But these are correlational. So we're looking at the associations. We're looking at how well one can predict another variable. If we want to actually say cause and effect, we have to do an experimental study. This is where we manipulate the independent variable in order to cause a change in the dependent variable. So I can say that a depression medication causes a decrease in depression symptoms. So I can manipulate the independent variable. I can give them the antidepressant, or I can give them placebo. And my hypothesis is that giving them the antidepressant will cause a change in their symptoms of depression. The people who got the placebo will not see that change. Now, experimental studies are a lot of times not feasible in psychology because things like IQ and depression and popularity, these things, I can't change them. I can't assign people to be popular or unpopular to see how if I'm saying that popularity leads to decreases in depression. I cannot tell some people to be popular and some people not to be popular. Instead, I have to look at a correlation. I can look at correlations between symptoms of depression and popularity and see that more popular adolescents are slightly less likely to be depressed. Now, of course, this is not the case for everyone, but this is really highlighting the difference between experimental and correlational. So experimental studies we will talk about throughout the semester, a lot of different experimental studies that we've used in psychology, but a lot of the understanding that we have of psychology is based off of correlational research because we can't assign a lot of those characteristics. The last part that I'm going to talk about with regards to the actual methods that we use in psychological research is research ethics. Now, this is the ethics of doing research. This is making sure that we are doing research in a way that is fair, that is good for people, that is good for humans as a whole, and is good for the participants. Now, psychology has a pretty checkered past. We'll talk about a number of different studies throughout the semester. Just a few examples of these are Milgram's obedience studies, Zimbardo's prison experiment, the Little Albert study. All of these were done in ways that were very unethical for different reasons. In terms of not allowing participants to stop the study when they wanted to, putting them in conditions that were not really humane, not getting permission even to do the study. So we'll talk about that with the Little Albert study. And so because of that, we work really hard to make sure that psychology today, the research that we do, is ethical. And we have lots of standards, we have lots of checks and balances, we have overarching organizations that look at all of the research that we're doing and make sure that it is ethical. So when we're doing this in humans, there are a few things that we want to make sure that we do. We have to obtain informed consent. What this means is that I can't just do a research study on you without your permission. I need to tell you what the study is about, and I need you to agree to be part of the study. You need to know everything that's going on and be able to make an informed decision about whether or not you want to participate. This is important because you need to know about it all up front. And so obtaining informed consent is important. This is especially true when we're looking at children or when we're looking at pregnant women or prisoners. These are considered three very vulnerable populations. So when we're looking at informed consent for children, we typically have to get agreement from the participant as well as consent from their parents. So it's legally binding in that respect. It has to have a legal adult to consent. We also want to make sure that we're protecting our participants from unnecessary harm. We have to justify the studies that we're doing. I can't just hook you up to an electric shock just to see what happens. I need to make sure that what I'm doing has a reason behind it, that I'm not putting you in any kind of unnecessary harm, that if I am, for instance, testing pain tolerance, that I'm only doing this to the extent that absolutely has to be done. And that if I want to test your pain tolerance, that it's being done for a legitimate reason, not just because, hey, I want to see what happens. I need to maintain confidentiality. Anything that you tell a researcher is confidential. They are, as researchers, I'm not allowed to tell anyone, I'm not allowed to give my participants reports to anybody, to the police officers, to anybody. So this is a very confidential thing. So even if you, for instance, I'm asking about substance use or sexual activity, or I'm asking about illegal behaviors, the police are not allowed to ask me for your answers. I'm not allowed to give them to them. I am bound by that confidentiality. They're not even allowed to subpoena them. So there is no way that the answers that you give in research are allowed to be tied back to you. So this is a way that we protect humans, because we want to be able to get true answers. So if I'm asking you questions about your sexual activity or illegal substance use, there's a reason. And I need to know your true answers in order to be able to do this study properly. And so in order to be able to do that, I have to have this confidentiality. I also have to debrief participants afterward. If there's any kind of deception that I'm using, and we'll talk about some of the studies that use deception later on in the semester, I have to let you know what the study was actually about. Most of the time, this deception is very benign and didn't really have any effect on you as a person, but I needed to kind of trick you into behaving naturally. And so in those cases, we have to debrief the participants afterward. We have to tell them what it was about. Now, with animals, this is a whole extra area of research ethics. We often use animals to study both human and non-human behaviors. So for instance, if I'm interested in the responses to stress, I can use animal models. I can use rodents, I can use cats or dogs, I can use chimpanzees in order to study this. I can also look at how these responses to stress relate to humans' responses to stress. They're also very valuable for animals because we can use research on how dogs respond to stress in order to improve the lives of dogs, not just of humans. We're not just focused on ourselves. We want to improve the lives of our non-human friends. So we have used research on stress and on bonding and things like that in order to improve the lives of shelter animals. So it's not just about using animals to make humans' lives better. We're also using this to help the animals. But we also have to make sure that we're protecting those animals, because they can't say, I do or do not want to be part of this study. They can't give consent. They can't understand what's going to happen to them in the study and decide that they want to be part of this. So instead, we have additional organizations that have very extensive guidelines to make sure that the treatment of these animals is humane and to minimize any discomfort that they're getting. So for instance, cats are often used in medical research, and the cats that are used in medical research are housed in kind of a shelter-ish area on the campus of whatever hospital or university is doing the study. And those cats have to be socialized. So every single day, someone has to go in and give those cats attention and play with them and pet them and make sure that they have a really good life. They have veterinarians who come in with the animals and make sure that the animals are a healthy weight, that they're not losing their hair, indicating that they're stressed. These animals actually get even more attention than a lot of humans do. They have a lot more people looking out for them than humans do because they're not capable of giving consent. And so there are entire organizations on each research campus making sure that those animals are being treated ethically. Now I'm going to talk a little bit about statistical reasoning. So if you've taken statistics, a lot of this is going to be familiar to you. If you haven't taken statistics, don't get overwhelmed. A lot of this is going to kind of go back to some of your college algebra stuff, or high school algebra stuff. So a lot of it's going to be pretty familiar, but I'm going to make sure that you know about this because it's going to be really important when we're talking about some of these later on. So to understand these measures of central tendency, of variability, of correlation, and of inferential statistics. So our statistics can generally be broken down into descriptive and inferential statistics. Descriptive statistics do exactly what it sounds like. They describe the data. So with these, we use measures of central tendency, measures of variability, and correlational coefficients. The first of these is measures of central tendency. Central tendency tells us what is normal. So for instance, here I have these data. I have the number 4, 6, 9, 1, 3, 0, and 4. Measures of central tendency are generally mean, median, and mode. The mean is the average. So we add up all of the numbers. Those numbers add up to 28. We divide by the number of numbers there is, so divide by 7, so that's 4. So you should be pretty familiar with the average. You've calculated the average since high school. The median is the middle number. So you can think of this, if you are driving down the road, the median of the road is the center of that road. It's that grassy part in between the two directions of the road. So the median, similarly, with numbers, is the middle number. So I put them in order by number. So I have 1, 0, 1, 3, 4, 4, 6, and 9. So I just put these numbers in numerical order. And then for the median, I'm going to go through and I'm going to find which one's the middle. So I have 0 and 9, I have 6 and 1, I have 3 and 4, and my middle number is 4. And then the mode is the most common number. So out of these, the only number that is repeated is 4. So that means our mode is 4. So in this case, the mean, the median, and the mode are all 4. So if all 4 of them are 4, or all three, mean, median, and mode are all 4, why bother using all 3? Now, all of them are 4 when there's a normal distribution, aka a normal curve. This means that some people are going to be over here at the extreme down here, some people are going to be at the extreme up here, but most people are going to be in the middle. This is also referred to as a bell curve. So with a normal distribution, the mean, the median, and the mode are roughly the same. But a lot of times we have what are called non-normal distributions. This is the example that we see here of this one. Boop. Sorry, I'm trying to do this on my laptop and it's weird. So a non-normal distribution, we see that a lot of the scores are going to be clumped at one end. So we have a lot of people here and then presumably fewer people here. We may have one person who's way out in left field. And what happens then is our mean and median and mode are no longer the same. So you can see the red, green, and blue lines here on this normal curve are all pretty much the same. Here, our mode is way off. Our median is still in the middle, but our mean is way up here. So we see this, for instance, when we look at household income in the United States. We talk about there being an income disparity or a wealth gap. And we see that really strongly when we look at that for the United States. So we see that the median, and this is why we talk about the median household income, because we have a lot of people who are going to be here. We have a lot of people who are going to be below the median, a lot of people who are poor, who are below the poverty line, or who are in that kind of middle class there. And then we have our Warren Buffetts, we have Bill Gates, we have Elon Musk, we have all of Jeff Bezos, we have all these people way out at this extreme who are knocking that mean way off to the side. Because think about, let's say every single person in your class, you have an exam, everyone makes around 70%. Or let's say everyone makes around 50%. This is a really hard exam. So everyone gets around 50%. We'll say some people get, most people get between 30 and 60%. And then you have that one person who gets 100%. Now, if I take the average, that one person's 100% is going to push the average this way, because that one person did really well, even though everybody else did about here. Now, the mode is the most common score. So if I have a lot of people who are bunched here, my mode is going to be the most common one. It's pretty low. If I have a whole bunch of people who got a 20%, one person made 100%, and a few people made a 30%, my average is going to be way up here. My mode is going to be way down here. My median is going to be somewhere in the middle. So this is why when we're looking at non-normal distributions, or where lots of people are bunched together either over here or over here, this non-normal distribution, this non-bell curve that we see here, we have to look at all three of those numbers. And that's when the mean, median, and mode are really going to be different from one another. Now for variability. Variability tells us how far apart the scores are spread. So we have our, if we're looking at the mean, for instance, that tells us our average score, but we want to know what the range of the scores was. So the range is the highest score minus the lowest score. Now the range is very sensitive to extreme scores. So let's say everyone got around 50%, one person got 100%, one person got 2%. That means that your range is going to be 98, because it's the highest score of 100 minus the lowest score of 2. So that's a range of 98. But most of the class, everybody except for those two people, got between 40 and 60. So the range can be really sensitive to those extreme scores. Now, if we didn't have those extremes, then everybody made between 40 and 60, our range would be 20. So a range of 20 versus a range of 98, that's a really big difference. But it does tell you what was the highest score that someone made, what was the lowest score someone made. Most cases, most exams, that range is going to be informative to you. You can tell kind of roughly where you fall, and if it was a really hard exam, if it was a really easy exam, things like that. We can also use what's called standard deviation. And standard deviation is used more commonly in actual statistics because it's not sensitive to those extreme scores. Now, what the standard deviation tells us is, in general, how far are participants from the average. So let's say the average here is 100. If everyone's really close to 100, so we see the range being from 60 to 120, we see most of our people are going to be kind of 80 to 110. This is our standard deviation. Our standard deviations can be pretty small. That means that all of our participants are pretty similar. Now, a large standard deviation, or this blue group here, means that there's a lot of variability. That means that, sure, maybe our average was the same, but the difference was much greater from our end scores to our mean. So this means that Some people, a lot of people are going to end up over here. A lot of people are going to end up over here. So that large standard deviation means that there's a lot of variability. It means that the average was still 100, but a lot of people are going to be kind of over here. So you can see that this looks much more flat because it's much more kind of evenly distributed across all the scores. Here, it's much more pointy because everyone did just about the same. So we use the standard deviation, and I'm not going to talk about how to calculate the standard deviation. You can learn that in statistics. I'm not going to teach you that right now. But it's important because it gives us a better picture of the scores than the range does, because you can still have a smaller standard deviation with one person way over here. It's not going to affect the standard deviation too much. And so the standard deviation tells us much more about, is it flat or is it a really pointy distribution? Next, we have correlations. So just like with correlational studies, we're looking at the relationship between two factors, two variables. And we're asking, can we predict one variable based on the other? Now, if two variables correlate, that means they move together. Now, again, this is not cause and effect. This is just the ability to predict one variable based on another. Now, we were talking about that in terms of correlational studies, looking at two variables that move together, like IQ and SAT score. But correlation is also a statistical test. So from that, we get what's called the correlation coefficient. Now, this is the value that we have assigned to the relationship. This is the physical number that tells us how much do they move together. Are they really close, where as one changes, the other one changes very similarly? Or are they kind of distantly related, so that one of them is kind of related to the other one, but not completely? And so our correlation coefficient ranges from -1 to +1. So -1 and +1 are the extremes. Now, a larger number, whether it's positive or negative, so we're talking absolute value here, a larger number means a stronger relationship. So either -1 or +1, these are very large in terms of absolute value. A correlation coefficient close to 0 means that it is a weak correlation, means that those variables don't really move together very well. To explain that a little bit more, here are the different types of correlations that we have. We have positive, negative, and no correlation. So a positive correlation is going to be a correlation coefficient greater than 0, and usually closer to 1. A positive correlation means that as one variable increases, so does the other. So a positive correlation would be, for instance, the correlation between the number of hours you study and your GPA. Because we know the more hours you study, the higher your GPA is. People who study very few hours here have a really low GPA. People who study a lot more tend to have a much higher GPA. And so we see this positive correlation. And now there are going to be a few people who don't have to study at all and still have a really high GPA. There are going to be people who study a lot and still get really poor scores on exams and things like that. That still happens, but in general, the more you study, the higher your GPA. Now, opposite of that is a negative correlation. This is whereas one variable increases, the other one decreases. So the more hours you spend playing video games, the lower your GPA gets. So people who spend very few hours playing video games are going to have higher GPAs. The people who spend a lot of hours playing video games are going to have low GPAs. Now, just like with studying and GPA, we see plenty of people who play video games all the time and still do really well. Some people who don't play video games at all and do really poorly. But in general, the more time you spend, playing video games, the lower your GPA is going to be, especially when you're in college. And because that generally means that the more time you're playing video games, the less time you're studying. So that's a negative correlation. So negative correlation, this one is going to be closer to -1. So this one's going to be closer to -1. This one's going to be closer to +1. And then we have no correlation. No correlation is going to be closer to 0. This means there's no association between the variables. So I can't really draw an upward line. I can't really draw a downward line. These dots are just kind of all over the place. So there's no association between the two variables. So for instance, the number of hours you spend picking your nose probably doesn't predict your GPA. There might be a little bit in there, but I mean, there are going to be plenty of people who pick their nose a lot and have a high GPA, plenty of people who pick their nose a lot and have a low GPA, plenty of people who don't pick their nose at all and have a low GPA, and plenty who have a high GPA. So, no association. This means that the correlation coefficient is closer to 0. So, remember back to here, we see that a larger number, either positive or negative, means a stronger relationship. This can go from -1 to +1. So these are types of correlation. So if I give you a correlation coefficient, I tell you that two variables are related with a correlation coefficient of 0.8, you would know that because that's positive, because it's 0.8, so positive 0.8, that it's going to be a positive correlation and that those variables are going to move together. If I give you a correlation of -0.7, you know that's going to be a negative correlation, so those variables are going to move in opposite. If I give you a correlation of 0.03, you're going to know that there's very little relationship between those two variables because it's really close to 0. In addition to our descriptive statistics, we also have inferential statistics. What inferential statistics allow us to do is determine whether something is statistically significant, which means that it is numerically unique. So if I give you the example, if you run a race and finish 15 seconds faster than someone else, would you say that you were significantly faster? This is going to depend. Was it a 100-meter race, in which case 15 seconds is a lot? Or was it 26 miles? Were you running a marathon, in which case 15 seconds one way or the other is probably not going to be much of a difference? Inferential statistics allow us to make inferences from our ability to infer from the numbers. So statistical significance is based on the individual score compared to everyone else's scores. And can we say that based on everyone else's scores, was this person unique? Now we do this using the mean, using the standard deviation, things like that. And statistical significance allows us to say that the difference between this individual and everyone else was likely not due to individual variation, to just chance, to a fluke. Now, another thing that we have to consider in with this is called practical significance. Now, we might see a statistically significant difference between oldest and youngest children on IQ of 3 points. That means that statistically, based on the numbers, based on means and standard deviations, older children have an IQ of 3 points higher than younger children. I don't remember if it's actually in this direction, but it's one way or the other. But IQ is 3 points of IQ isn't very much. We consider the standard deviation to be 10 points for IQ. And we really don't consider really substantial differences in IQ until we're at 2 standard deviations. So we're looking at 20 points, 20 IQ points, before we're really noticing any difference in people. So 3 points, although it's statistically significant, it really has no real world practical significance. The last part about it I'm going to talk about for this lecture is improving the reliability of statistics. So we have all of these numbers and they tell us a lot of information, but how can we make sure that what we're getting out of these studies is reliable? We want to make sure that we're using representative samples rather than bias samples. If we only test people at Harvard, likely won't tell me a lot about the study habits of all college students. Now, I could find statistically significant differences between psychology majors and business majors and biology majors, but if I'm only looking at Harvard, that might not tell me very much. So I want to make sure that the differences that I'm finding in my study are actually going to be representative of everyone in my population. I also would like less variability. Having less variability is more reliable than having more variability. So if you're consistent, it's easy to tell when something is markedly different. So if you get consistently about 85% on all of your exams, getting a 45% on an exam would be really unusual. Now, if you range from 40% to 90% on exams, if you are all over the place, 45% might not be unusual. And so being able to be consistent allows us to know when something is unusual, allows us to know when something's unique. And finally, more cases are better than fewer cases. If you see a restaurant who has a review on Yelp, just a single review, whether that review is really good or really bad, you're not going to trust it as much as a restaurant that has 500 reviews on Yelp. So if you're shopping on Amazon and you see two products that are pretty similar and they have the same price and they're basically the same product, and one of them has a single 5-star review, no other reviews, just one review that was 5 stars, and you see another product that has 3,000 reviews and has an average of about 4.5, I don't know about you, I would trust those 3,000 reviews of a 4.5 more than that one person who gave a 5-star review. So it's the same thing with statistics. Having more cases is better than having fewer cases in general. So these are things that we can do to improve the reliability of our statistics, and therefore our reliability in being able to say that what we found is really going to be true for everyone. So it improves our research in general as well. So this is going to be the end of this lecture, and then we will pick up next time talking about neuroanatomy and physiology.